Welcome back. Let's learn about the chain rule for multivariable functions. All right, so today we're going to extend the concept of the chain rule for derivatives of single variable functions from Calculus 1 to multivariable functions here in Calculus 3. Now you might be thinking, wait, didn't we already do this? Haven't we already used the chain rule multiple times throughout different examples of finding partial derivatives? And well, the answer is yes, but also no. Let me explain. All we have used so far is the chain rule from Calc 1 that looks like this. If you want to take the derivative with respect to x of a composite function where you have f of g of x, where f is the outside function and g of x is the inside function, the derivative is equal to the derivative of the outside function, keeping the same inside function, so f prime of g of x, multiplied by the derivative of the inside function, g prime of x. Alright, so this is the chain rule that you were very familiar with using by this point, but when we first developed this formula in Calculus 1, it may have looked a little bit different. What we could do is express this composite function in a slightly different way. Instead of representing it with one expression, we could represent it with two different expressions, or two different equations. We could let y equal a function in terms of a variable u, where u is then equal to that inside function of g of x. All right, so we're still representing the same function here. We're letting y equal that function f, where the inside function is then just u, but where u is equal to g of x. Okay, so you could replace g of x for u in this function, and you still have the same composite function. For example, here is a composite function where if we wanted to find the derivative of y with respect to x, we would need to use the chain rule. The inside function is x plus 1, and the outside function is the quantity cubed. And so another way that we could rewrite that composite function is with two equations like this. We could say that y is equal to u cubed, where then u is equal to x plus 1. Right? If you plug x plus 1 in for u in this expression, you get back to the original composite function. Y is equal to x plus 1 quantity cubed. Okay, so this is just a different way of expressing the same composite function, but regardless of how we represent it, y is still the dependent variable and x is still the independent variable. But notice that when we rewrite the composite function like this, there is a third variable of u. What is that? Well, we would call that an intermediate variable. An intermediate variable acts as a bridge between the dependent variable and the independent variable. Right, the variable of u gives y access to the independent variable. It provides a pathway from y to x. Y is equal to u cubed, but u is equal to x plus 1. And when we express a composite function like this, we can express the chain rule in a slightly different way. And this is what I was referring to earlier. This is maybe the first way that you were introduced to the chain rule in Calculus 1. Because if we want to find the derivative of y with respect to x using these two equations, here's what that would look like. We'd have dy dx is equal to the derivative of y with respect to u. In other words, the derivative of the outside function. So we would have dy du, and then we would multiply by the derivative of the inside function, which would be the derivative of u. We take the derivative of u with respect to x. And so you'd multiply by du dx. All right, and notice here that technically these du's could be canceled out, and so dy dx would be equal to dy dx. So we know that this is true. All right, this is another way to express the chain rule for derivatives of single variable functions from Calculus 1. Both of these two ways will work, right? If we were to use our traditional method here to take the derivative of this composite function, we could take the derivative of the outside function, so use the power rule, multiply 3 down, subtract 1 from the exponent, and then multiply by the derivative of the inside function. The derivative of x would be 1, and the derivative of 1 is 0. So we know that dy dx is equal to 3 times x plus 1 squared, right? That would be the derivative of y with respect to x using this method, but we could also find that same derivative using this formula. If we start by taking a derivative of y with respect to u, that would be this right here, dy du would be 3u squared, right? So dy dx is equal to 3u squared, and that would be multiplied by the derivative of u with respect to x. And the derivative of u with respect to x would just be 1. The derivative of x is 1, and the derivative of 1 is 0. So you're multiplying by 1, but that doesn't change anything. You would still have 3u squared, but then you would want to express that derivative in terms of x, so you would replace u with what it's equal to, which is x plus 1. So dy dx is still equal to 3 times x plus 1 squared. Okay, so both methods work. The chain rule can be done in either of these two ways. It doesn't matter if you work with a composite function, where it's just in terms of the dependent and independent variables, or if you use it when working with an intermediate variable as well. It works both ways. And actually, we revisited this idea in Calculus 2 with parametric derivatives. Remember that in Calculus 2, if we had a set of parametric equations, x is equal to f of t and y is equal to g of t, that the derivative dy dx, or the derivative of y with respect to x, is equal to the derivative of y with respect to t divided by the derivative of x with respect to t. It looks different at first compared to our chain rule from Calculus 1, but if you were to slightly rewrite this by remembering that dividing by a fraction is the same as multiplying by the reciprocal of that fraction, you could also say that dy dx is equal to dy dt multiplied not by dx dt, but by dt dx, right? Flip the numerator and denominator, and multiplying by that fraction would be the same as dividing by this fraction. All right, so we'd multiply by dt dx. So the derivative of y with respect to x would be equal to dy dt times dt dx. Technically, those dt's would cancel out, just like the du from earlier, and you would still have dy dx is equal to dy dx. Okay, that was the idea of a parametric derivative. In this case, we would still treat y as the dependent variable and x as the independent variable, but then t, what we would usually think as the parameter for the parametric equations, really is acting as the intermediate variable in this case. All right, for example, here I have a set of parametric equations, x equals t minus 1 and y equals t cubed. You could rewrite this first parametric equation here by solving for t. You could add 1 to both sides of the equation and have t is equal to x plus 1, and that would be paired with y equals t cubed. You could then replace t in this equation for y with what it's equal to here, and get the composite function that y is equal to x plus 1 cubed, right? The same exact composite function from earlier. All right, really what we did here is eliminate the parameter, something that we learned how to do in Calculus 2, but through that process, we are treating t as the intermediate variable, the variable that acts as a bridge between the dependent variable y and the independent variable x. Okay, so really, when we're taking a parametric derivative, we are once again making use of the chain rule, but where that parameter t is the intermediate variable. And so I show you all of this for one reason. And that is to prove the point that whether we were working with the chain rule in Calculus 1 or whether we were working with it in Calculus 2, in both of these cases, we were always working with one intermediate variable, and that intermediate variable is always defined in terms of one independent variable. Okay, there's only one of each type of variable. There's always one dependent variable, that's not going to change, but in these instances where we have been using the chain rule, there has only ever been one intermediate variable and one independent variable. Okay, and so when we extend the chain rule to multivariable functions here in Calculus 3, what's actually going to extend, or what's going to change here, is one of those two numbers, or possibly both. We will either change the number of intermediate variables, meaning that there will be more of them, and or we will change the number of independent variables. Okay, so it could be one or the other, or both at the same time, but when this is the case, our chain rule from Calculus 1 no longer applies. We need to extend that chain rule to account for these other cases. And so, let's take a look at how we will extend the chain rule for these other cases by first considering the scenario where we keep one independent variable but expand to two intermediate variables. Okay, so consider the following equations here. We have w is equal to x squared plus y squared, where x is equal to t squared and y is equal to t cubed minus 1. In this example, w is our dependent variable. It is defined as a function in terms of two variables, x and y. So we would view w as a multivariable function. But then both of those variables, x and y, are defined in terms of another variable, right? X is defined as being t squared, and y is defined as t cubed minus 1. In this case, t is acting as the independent variable, while x and y are the intermediate variables. They are acting as bridges or pathways from the dependent variable w to that independent variable of t, right? You could plug in this expression for x in terms of t into this x in this function, and you could do the same thing for y. You could plug what y is equal to in terms of t in for y right here, and then after doing both of those substitutions, you would have a function of w entirely in terms of t, the independent variable. And so if we wanted to find the derivative of w with respect to that independent variable t, so in other words, if we want to find dw dt, we will need to use the chain rule, but it will look a little bit different since we are now dealing with two intermediate variables. And so what does that look like? How do we find the derivative of w with respect to t? Well, I want to show you the reasoning behind it before I just give you the formula. I want to sort of develop it here for you. And so what I first want you to realize is that as the values of t change, or as there is a change in t, both x and y are going to change. And as a result of x and y changing, so will w, because w is dependent on x and y, but then x and y are dependent on t. So when t changes, x and y change, and that results in a change in w. And remember that a derivative is the rate of change of the dependent variable with respect to the independent variable. So if we want to consider dw dt, we will have to consider how x and y, the intermediate variables, are being affected by changes in t. Okay, so here's how I would think about the change in w. The change in w would be equal to the amount by which x changes w, right? Because when x changes, w will change. So you have to take that into account, but then you want to add that to the amount that y would change w. Okay, both of those intermediate variables are in terms of that independent variable t, and when t changes, both x and y change, and both of those changes will have an effect on w. So to get the overall change in w, we have to take into account the amount that each of those intermediate variables change the value of w. So you take the sum of those two changes. Then what we can do is find a way to express these amounts of change with some mathematical expressions. Okay, so to take this one step further, how could we find the amount that x changes w? Well, one way that you could do it is by considering the change in x and then multiplying that by the rate of change of w in the x direction. All right, so I'm going to write that down here, and then I'll explain what that means. We'll have a rate of change for w in the x direction multiplied by the actual change in x. All right, so what this means is that x is going to change by some amount when t changes, and that will result in some change delta x, and the amount by which that changes w is dependent on the rate of change for w in terms of x, right? There'll be some rate that w changes by some amount for each change in x. Well, you would multiply that rate by the actual amount of change in x to get the total change in w with respect to x. All right, and so you could do the same thing for y. The amount that y changes w could be found by taking the rate of change for w in the y direction multiplied by the actual change in y, right? When t changes, there will be some amount of change in y, that would be delta y, and to figure out how much that will change w, you want to take the rate by which w changes with respect to y and multiply that by the amount of change in y. If w changes by some amount every time y changes, you just multiply that rate by the actual change in the y, and that will give you how much w changes with respect to that variable. Okay, so there's two pieces here. There's one for each intermediate variable. We have a piece for x and a piece for y. But now to get even closer to a mathematical expression that we can use, we need to think of a way to represent the rate of change for w in the x direction and y direction, which if you're thinking about what we have learned recently in Calculus 3, that perfectly describes a partial derivative, right? A partial derivative of a multivariable function will give you the rate of change for that multivariable function, but with respect to just one of the variables, holding the other variable constant. The partial derivative with respect to x of a multivariable function gives you the rate of change for that function in the x direction, just like the partial derivative with respect to y would give you the rate of change for that function in the y direction. So each of these two rates of change could just be represented with partial derivatives, specifically partial derivatives of w. Okay, so what we get here is that the change in w is equal to a partial derivative of w with respect to x multiplied by the change in x plus the partial derivative of w with respect to y multiplied by the change in y. All right, and so now we have a nice mathematical expression, but we're not quite there yet. We're still looking for a formula to help us find dw dt, right, the derivative of w with respect to the independent variable t, and notice that there currently are no t's in this equation. So we need to involve t somehow, right? We want to introduce it to this equation so that hopefully we can get to an expression that will help us find dw dt. And specifically, we want to consider the change in t. And so what we could do here is divide both sides of the equation by the change in t, or delta t. And so if we do that, we'll get delta w divided by delta t is equal to the partial of w with respect to x multiplied by delta x divided by delta t plus the partial of w with respect to y multiplied by delta y divided by delta t, right? Whatever you do to one side of the equation, you have to do to the other side. So it is totally legal to divide both sides of the equation by delta t. And now, remember that we are trying to find a derivative here, dw dt. And if you recall, in the definition of a derivative, we are looking at the limit as the change in the independent variable approaches zero, right? We used to look at the limit as delta x approaches zero for a derivative of a single variable function. We could do the same thing here. Let's take a look at the limit as delta t approaches zero of both sides of the equation, because t is the independent variable. And so let's work on that next. If we take the limit of both sides of the equation, we will end up taking the limit of each of these terms individually. So we'll have the limit as delta t approaches zero of delta w divided by delta t is equal to the limit as delta t approaches zero of the partial of w with respect to x multiplied by delta x divided by delta t. And that will be added to the limit as delta t approaches zero of the partial of w with respect to y multiplied by delta y divided by delta t. All right, now in each of these limits, notice that we are just looking at the limit as delta t approaches zero. So that's really all we're worried about here, delta t. So when you look at these two limits here, these partial derivatives have nothing to do with t, right? It's the partial of w with respect to x and the partial of w with respect to y. So when we're considering delta t, those two values would just be considered as constants. What we can do is pull those out of the limits. They're not going to be affected by that limit in any way. So I'm going to quick change that here. I'm going to pull this partial out front of this limit and this partial out front of this limit, and that will look like this. We'll have the partial of w with respect to x multiplied by the limit as delta t approaches zero of delta x divided by delta t, and then the partial of w with respect to y multiplied by the limit as delta t approaches zero of delta y divided by delta t. Now, you might be wondering, well, why didn't we pull out the delta x and the delta y? That's because both x and y are directly affected by the change in t, right? The change in x and the change in y depends on the change in t. And if you take another look at these limits, they should look pretty familiar. What we have in each of these cases is actually the definition of a derivative, right? Remember that dy dx for a single variable function, the derivative of y with respect to x, we would define that as the limit as delta x approaches zero of the change in y divided by the change in x, right? And we would define the change in y as f of x plus delta x minus f of x, or y of x plus delta x minus y of x. But either way, that is the definition of a derivative, specifically a derivative from calculus 1, so we could apply the same thing here. The limit as delta t approaches zero of delta x divided by delta t would just be the derivative of x with respect to t. Just like this limit as delta t approaches zero of delta y divided by delta t would be the derivative of y with respect to t. Okay, not to mention that we also have one more over here. We have the limit as delta t approaches zero of delta w divided by delta t. That would be the derivative of w with respect to t, the exact derivative that we are trying to find, right? The derivative of w, the dependent variable, with respect to t, the independent variable. Okay, and so our final equation looks like this. We find that dw dt is equal to the partial of w with respect to x multiplied by the derivative of x with respect to t, and that is a regular derivative, not a partial derivative. So use the regular d's there, and then that is added to the partial derivative of w with respect to y multiplied by the regular derivative of y with respect to t. Again, that is not a partial derivative, that is a regular derivative. Just like dw dt is not a partial derivative, it is a regular derivative. It is a derivative of w with respect to t. And what we have found here is the chain rule for multivariable functions, at least the most basic form, right? When we're working with two intermediate variables. Okay, as you'll see in just a little bit, we can expand this formula. But to summarize what we've done so far, the chain rule, when you're working with one independent variable and two intermediate variables, looks like this. You have a multivariable function, w is equal to a function in terms of x and y, where both x and y are functions of t, g of t and h of t. For those three functions, the derivative of w with respect to t, the dependent variable with respect to the independent variable, is equal to the partial of w with respect to the first intermediate variable multiplied by the derivative of the intermediate variable with respect to the independent variable plus the partial derivative of w with respect to the second intermediate variable multiplied by the derivative of that intermediate variable with respect to t. Okay, and so let's see this in action. What does it look like when we actually use this chain rule? Well, if we go back to our example, let's use this chain rule to actually find dw dt for this function. W is equal to x squared plus y squared, where x is equal to t squared and y is equal to t cubed minus 1. What we want to do first is find the partial derivative of w with respect to x. So let's do that here. If we're taking a partial with respect to x, then that means that we're treating the other variables as constants. So that means y would be a constant. So the partial of w with respect to x would be equal to 2x, right? The derivative of x squared is 2x, and then the derivative of y squared, a constant, would be 0. Then let's find the other partial derivative. Then we'll move on to the regular derivatives. So let's find dw dy. Let's take a partial of w with respect to y. In that case, we'll treat x as a constant. So the derivative of x squared is 0, but then the derivative of y squared is 2y. Okay, so that's our two partial derivatives. Now let's find these regular derivatives. Let's take the derivative of x with respect to t. The derivative of t squared would be 2t. So dx dt is 2t. And then let's find the derivative of y with respect to t. And so dy dt would be equal to the derivative of t cubed minus 1. Use the power rule on t cubed, and you get 3t squared. And then the derivative of negative 1 is 0, because that is a constant. Okay, but then putting all these pieces together, here's what we get for the derivative of w with respect to t, or dw dt. It will be equal to the partial of w with respect to x, which is 2x, so I'll write in 2x, multiplied by dx dt, which is 2t, so I'll write in 2t, and then add that to the partial of w with respect to y, which is 2y, so we have 2y, and then that is multiplied by dy dt, which in this case is 3t squared. So we're multiplying by 3t squared. Okay, so then simplifying, 2 times 2 is 4, so we get 4 times x times t, plus 2 times 3 is 6, so we have 6y t squared. And that right there would be dw dt, at least if you keep it in terms of x, y, and t. Okay, this is technically a correct answer, and depending on the functions that you're working with, you might want to keep it in this form, because even though it's not entirely in terms of t, which you might think it would be since it's dw dt, technically it still is in terms of t because both x and y are defined in terms of t. Okay, so while you could keep it like this, you could also rewrite it such that it is entirely in terms of the independent variable t by replacing x and y with what they are equal to in terms of t. Okay, so if we did that here, you would replace x with t squared, so this would be equal to 4t squared times t plus 6 times y, which we would replace with t cubed minus 1, so we have t cubed minus 1, times t squared. And then simplifying, we have 4t cubed plus 6t squared distributed through this quantity. T squared times t cubed is t to the power 5, and then negative 1 times t squared would be negative t squared. So altogether, you get 6t to the power 5 minus 6t squared. All right, so that would also be a correct answer for dw dt using the chain rule. This is just the version that is entirely in terms of the independent variable, which can be convenient to find or use sometimes depending on the situation. All right, and so now that you have the derivative of w with respect to t, you could use it for different applications. One thing that you may want to do is evaluate that derivative at a specific value of the independent variable. So let's say we wanted to know what the value is at t equals 1. We could plug 1 in for t in this expression directly if you have this version of the derivative, so that would be pretty simple. Or if you left your derivative in this state, you could still plug 1 in for t for these two t's, but then to figure out what x and y would be when t equals 1, you just want to plug t equals 1 into those expressions for x and y, and then those values would go into this expression. Okay, so you could do it that way, but since we have dw dt entirely in terms of t, I would just plug 1 in right here. So what we would have is dw dt evaluated at t equals 1 is equal to 4 times 1 cubed plus 6 times 1 to the power 5 minus 6 times 1 squared. In each case, 1 cubed, 1 to the power 5, and 1 squared are all equal to 1. So we get 4 times 1, which is 4, plus 6 times 1, which is 6. So 4 plus 6 is 10, minus 6 times 1, which would be 6. So 10 minus 6 gives you an answer of 4. All right, so that would be the value of dw dt at t equals 1. And you would get the same answer of 4 if you plug t equals 1 into this form of the derivative, remembering to also plug in 1 for t in the expressions for x and y, and putting all of that together. Hey, real quick, before we get to the next part of this lesson, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. Okay, now something that you might find helpful to visualize the chain rule, especially as we change the number of intermediate and independent variables in just a little bit, is to draw a diagram or what is called a derivative tree. And so here's what that looks like. If we continue on with our same example from earlier, what we want to do is organize the different variables in these equations. Remember that we have one dependent variable of w, two intermediate variables of x and y, and one independent variable of t. And so what you want to do to draw this diagram, or this derivative tree, is make three different columns for those different variables. So that might look something like this. We have the dependent variable, the intermediate variables, and the independent variables. You want to put them in this order because remember, the intermediate variables act as a bridge between the dependent and the independent variables. So let's write in what we have here. Remember that w is our dependent variable, and then x and y are the intermediate variables. So I'll write in x and y, and then we have one independent variable, t. Both x and y are defined in terms of t. Okay, so we have one independent variable. And now what you want to do to finish off the derivative tree is just draw some connecting lines between the different variables. From w, we have a pathway to x and a pathway to y, and then from each of those intermediate variables, we have one pathway to t. We can go from x to t and from y to t. And from this diagram, we can now form the chain rule formula. In this case, we would be finding the derivative of w with respect to t, right? There's one dependent variable, that will always be the case, and there's only one independent variable, so the derivative in this case would just be dw dt. But to find that, what we do is we start by looking at w in this chart, And then consider the different pathways that we have. From W, we have a choice. We can either go to X or we can go to Y. When you have a choice, when moving from one variable to another within this diagram, that indicates that you will be taking a partial derivative with respect to the variable that you are moving to, right? So for example, if we go from W to X, we had to make that choice. We could have went to Y as well, but we're not this time. We're going from W to X. That is a choice that we made, so that will be a partial derivative, specifically the partial of W with respect to X. All right, so we write that down first. We have the partial of W with respect to X. And then now that we are at X, we will move to the next type of variable, and we only have one option. We can only move from X to T, so that indicates that we have a regular derivative. So from X to T, we only have one option, and that is to take a derivative of X with respect to T. And so we will multiply our previous partial derivative by that regular derivative. So we multiply by dx dt. And so that term is done. We moved from the dependent variable to the independent variable, but we still have to consider the other pathway, right? We just took care of the pathway using x, but now going back to the dependent variable, we're going to use the other pathway, where we move to y. And so when you go to the different intermediate variable, you will then be adding that other term, all right? So we're going to be adding the derivatives that we get when moving from w to y to t, right? From w to y, we had to make a choice there. We could have gone to x, but since we didn't and we went to y, that will be a partial derivative. So we have the partial of w with respect to y. We can write that in here. We have the partial of w with respect to y, and then we're multiplying by the next derivative when we move from y to the independent variable, which in this case is t. And there's only one option, right? We can't go anywhere else. Y only leads to t, and so that means it will be a regular derivative. So that would be dy dt. And so that's what we would multiply by that partial derivative. Okay, and so now you can see we have developed that same chain rule formula from earlier. We didn't have to memorize it. Instead, we could just draw out this derivative tree and use that to help us form that equation. Okay, and this will be very helpful moving forward because what we want to look at next is when we expand what we've already worked with here. For example, what do we do when there are more than two intermediate variables, right? What if we increase the number of intermediate variables for the multivariable function? Well, it's a pretty easy adjustment. If there are more intermediate variables, all you have to do is add another term to that chain rule formula for each of the intermediate variables. All right, so for example, let's say we have this multivariable function, w is equal to xy plus xz plus yz, where x is equal to t minus 1, y is equal to t squared minus 1, and z is equal to t. All right, so notice here that this multivariable function is in terms of three intermediate variables, that being x, y, and z. And each of those intermediate variables are defined in terms of one independent variable, that being t. Okay, so making a derivative tree here, we have one dependent variable of w, and then we have three intermediate variables, that being x, y, and z. And then all three of those intermediate variables are in terms of one independent variable. So you could choose to write that like this, just draw one t, or if you're drawing the pathways, sometimes it's easier to draw a t for each of the intermediate variables. But then if we were to use this tree to create our chain rule formula, remember that we still want to take a derivative of the dependent variable with respect to the independent variable, which is t. So we're still looking for dw dt here. What would that be equal to? Well, we're going to have three terms for that derivative because we have three intermediate variables. We have three choices from w. We can go to x, we can go to y, or we can go to z. And so when we make each of those choices, since it is a choice, we will be taking a partial derivative of that dependent variable with respect to those variables. Okay, so each of those lines represents a partial derivative, while each of these lines, there's no choice here. You can only go from x to t, or from y to t, or from z to t, and so those are regular derivatives. Okay, the d's are not as curly as these. But if we start with the first term, we'll take a partial of w with respect to x, and then multiply it by the regular derivative of x with respect to t. So we'd have dw dx times dx dt, where one is a partial, but the other is not, And then we would add that to the next term where we take a partial with respect to y and then a regular derivative of y with respect to t. So that gives you dw dy times dy dt. But then we're not done. Now comes the extension for the third intermediate variable, that being z. We will now take a partial of w with respect to z and then a regular derivative of z with respect to t. So we'd have a partial of w with respect to z multiplied by dz dt. Okay, so that would be our formula for the chain rule in this case, where w is defined with three intermediate variables that are all defined with one independent variable. Notice that we didn't have to memorize this. We were able to develop this formula by drawing out this derivative tree using the different variables that we noticed in these given equations. Okay, but now if we actually want to find dw dt for this example, here's what that would look like. Let's start by finding the partial of w with respect to x. So looking at w here, we will be treating y and z as constants. So the derivative of this first term with respect to x would just be y, because the derivative of x to the first power is just its coefficient, or the constant multiplied by it. So we get y, and then don't forget about the other terms. The derivative of x times z with respect to x would just be z, and then this last term, that is a constant with respect to x, so its derivative is 0. So we get y plus z as the partial of w with respect to x, and then we're multiplying by the derivative of x with respect to t. And so that would be right here, the derivative of x with respect to t. This is a regular derivative. The derivative of t would be 1, and the derivative of -1 is 0, so we're multiplying by 1. And then that would be added to the partial derivative of w with respect to y. So now we're going to treat x and z as constants for w. For the first term, the derivative of y to the first power will just be equal to its coefficient of x. So we get x plus 0, because x and z are constants, so that term just becomes 0. But then for the last term, the derivative of y to the first power will be z, that constant or coefficient for that term. So for the partial of w with respect to y, we get x plus z, and then that will be multiplied by dy dt, the regular derivative of y with respect to t. So the derivative of t squared is 2t, and the derivative of -1 is 0. So we multiply by 2t, and then we will add that to the partial of w with respect to z, so x and y will now be treated as constants. So this first term is a constant whose derivative is 0, and then the derivative of x times z will just be the coefficient of z to the first power, which is x, and the derivative of yz will be y. All right, so we get x plus y, and then we want to multiply by the derivative of z with respect to t. And so we have z equals t, the derivative of t is 1. So we multiply by 1. All right, and so now what we want to do is simplify. dw dt will be equal to y plus z plus 2t distributed through this quantity. So we get 2x times t plus 2z times t plus x plus y. All right, now you could leave it in this form. That would be totally fine. This would be the right answer for dw dt because x, y, and z are all defined in terms of t, so this is okay. But if you want to explicitly write it out in terms of t, that can be helpful. And I would always recommend you do that if it's easy enough to do it. Sometimes you'll have very complicated expressions for w, x, y, and z, and so it might not be worth it. But in this case, this is not too bad. So I'm going to plug in what x, y, and z are equal to in terms of t into this expression. All right, so let's finalize our answer here. This would be equal to y, which is t squared minus 1 plus z, which is t. So we have t squared minus 1 plus t, and then plus 2xt, where x is t minus 1. So we have plus 2 times t minus 1 times t, plus 2 times z times t, where z is t. So you'll have 2 times t, which is t squared. So we have 2t squared. And then we're adding that to x plus y. So we just replace x with t minus 1 and y with t squared minus 1. So we have plus t minus 1 plus t squared minus 1. All right, then simplifying, we have some like terms that can be combined. Notice that we have a t squared here, a 2t squared here, and another t squared right there. So together we get 4t squared. Then we also have a t right here and a t right here. So we have plus 2t. And then we also have a -1, a -1, and another -1, which gives us -3. And then finally, let's distribute 2 through this quantity and t through that quantity as well. So multiply 2t by t and -1, and you get plus 2t squared minus 2t. All right, and so then positive 2t and negative 2t cancel out, and 4t squared plus 2t squared is 6t squared. So you get 6t squared minus 3. And that right there would be dw dt, the derivative of w with respect to the independent variable t. It's 6t squared minus 3. Okay, so that's how you take care of more intermediate variables when working with the chain rule. But what if there are more independent variables? Well, if there are more independent variables, you can no longer find a regular derivative dw dt. Instead, you will be finding two partial derivatives of w, okay, because there are more than one independent variable. So for example, here we have w is equal to x cubed plus y cubed, where x is equal to t squared plus s squared, and y is equal to 3ts. All right, so in these equations, we have the main function with the dependent variable w that's equal to an expression with two intermediate variables, x and y, where x is defined in terms of two independent variables and y is defined in terms of those two independent variables as well. So if we draw out the derivative tree, we still have one dependent variable of w that will never change, and then we have those two intermediate variables, x and y. So we have a pathway to both x and y from w. But then for both of those intermediate variables, there are two independent variables. There's an independent variable of s and an independent variable of t. And I'm going to write those down for both of those intermediate variables. All right, so from x, we have a pathway to s and a pathway to t. And then from y, we have a pathway to s and a pathway to t. And because of those different branches in this tree, the formula for the chain rule is going to look different. Specifically, what's going to happen is all of the derivatives that we will take will be partial derivatives. There are no more regular derivatives here because there are multiple independent variables. Okay, and so back to what I was saying earlier, we're not just going to be finding one derivative anymore, dw dt. That is gone. Now we have to find two partial derivatives, one for each of the independent variables. Okay, the number of independent variables in your tree will tell you how many partial derivatives you have to take. In this case, we just have s and t, so that means that there will be two partial derivatives for w. Okay, or if you don't like drawing the tree, you can always look at the equations for the intermediate variables and count the number of independent variables, and that will also tell you how many partials there will be. All right, so in this case, we want to find a partial of w with respect to s. That is one of the derivatives that we want to find. So we have a partial of w with respect to s, and that will be equal to some formula that we will set up in just a second. And we will also have a partial of w with respect to t. All right, so let's work on one at a time. Let's start with the partial with respect to s. We're starting at w, and we have a choice between x and y. So there will be two terms for this formula, meaning that both of them will be partial derivatives. But let's start with our choice of x. Once we get to x, we have two choices. But remember, we're taking a partial of w with respect to s. So for this formula, we're just going to consider this pathway. All right, it's still going to be a partial derivative, but we are going to take this route for the first term of this partial derivative. Okay, it's dw ds, so don't care about the t's right now. We're just focusing on the pathways that take us to that independent variable of s. So first of all, we'll take a partial of w with respect to x. That will be dw dx, and that will be multiplied by the partial of x with respect to s. So we have a partial of x with respect to s. And then we will add that to the other term where we work with y, the other intermediate variable. Okay, we don't include the partial of x with respect to t. Remember, we're not going to work with t's at all for this partial derivative. We're just focusing on s for now. So what would the other pathway be? Well, we're going to go to y by taking a partial of w with respect to y, and then we'll take a partial of y with respect to s. All right, there would be another partial here, just like there'll be a partial here and here when going from x to t and from y to t. But again, we're just focusing on this pathway right now that takes us from w to s. We have to consider all pathways that we can take to get to s within this tree. We already took care of one of them. Now let's take care of the other. So we'll have a partial of w with respect to y. So we'll write that in here. And then that will be multiplied by a partial of y with respect to s. So we have a partial of y with respect to s. And that completes our first equation, or first formula, for the chain rule here when working with two independent variables. Now let's move on to the other one. We found dw ds, now let's find dw dt, or the partial of w with respect to t. So now we will consider the other paths we have not taken yet. So we'll start at w, go to x, and then to t. All right, so we move from w to x, and then from x to t. So we still take a partial of w with respect to x. That part does not change, but then we do multiply by a different partial derivative when going from x to the independent variable, because now we're considering t, not s, so we'll take a partial of x with respect to t this time. So you're multiplying by a partial of x with respect to t. And then you'll add that to another term involving the intermediate variable y, because the other pathway that we can take will be from w to y, and then from y to t. All right, so we'll take a partial of w with respect to y, giving us dw dy. Again, that is the same as it was before, but what's different is the next derivative, or that next partial derivative. Instead of taking a partial of y with respect to s, we will take a partial of y with respect to t. So we get dy dt. All right, and there we have it. Those are the two formulas that we will use via the chain rule to find the partial derivatives of w with respect to the two independent variables. Okay, and so now that we have those set up, let's finish this example. Let's find these two partial derivatives. Let's start with dw ds, where we take a partial of w with respect to x. So looking at w here, we'll treat y as a constant. Just take the derivative of x cubed, and you'll get 3x squared. The derivative of y cubed would be 0, because we're treating it as a constant. So we have 3x squared multiplied by the partial derivative of x with respect to s. So looking at x here, you would treat t as a constant and differentiate s. So t squared, the derivative of that is 0, but s squared, the derivative would be 2s. So we're multiplying by 2s, and then you add that to the partial derivative of w with respect to y. So treat x cubed as a constant. That derivative will be 0, but the derivative of y cubed would be 3y squared. So we have 3y squared, and then that will be multiplied by the partial of y with respect to s. So looking at y here, if we're taking a partial with respect to s is to the first power, its derivative will be its coefficient, which would be 3t, including that t, because t would be a constant. So we're multiplying by 3t. Okay, and so that's pretty much it. We can simplify it a little bit by multiplying those constants. But for the sake of completion, I'm also going to replace x and y with what they're equal to in terms of s and t. Okay, so we would get 6s, that is just 2 times 3, which is 6, and then I'm putting that s right there. And then x squared would be this quantity squared. So we have t squared plus s squared squared plus 3 times 3 is 9. So we have 9, and then I'll pull that t out front, that being this t right here, just pulling that out with the 9. And then y squared would be this quantity squared, so you'd have 9t squared s squared being multiplied by this quantity, and 9 times 9 is 81. T squared times t is t cubed, and then just include that s squared on the end. So altogether, you get 81 times t cubed times s squared. That is the partial of w with respect to s. Now let's find the partial of w with respect to t. And we can reuse some of our work from earlier because we will need the partial of w with respect to x again and the partial of w with respect to y. So we don't have to do those again. We will still have 3x squared, but now it's going to be multiplied by the partial of x with respect to t, not s. So going to x here, if we're taking a partial with respect to t, treat s as the constant, and so this term, the derivative would just be 0, but the derivative of t squared would be 2t. So we multiply by 2t, and then add that to the partial of w with respect to y, which we already found before. It's 3y squared, but then that would be multiplied by the partial of y with respect to t. So looking at y here, treat s as the constant. The derivative of t to the first power would just be its coefficient, which would be 3 times s. so we multiply by 3s. All right, and then simplifying once again, you could keep it in this form, but I am going to try to get it back into terms of s and t by replacing x and y with what they're equal to in terms of s and t. So let's do that here. 3 times 2 is 6, carry over that t, and you get 6t, but then x squared once again would be this quantity squared. So you'll have t squared plus s squared squared, and then that will be added to 3 times 3, which is 9, times s, so you have 9s, but then once again you're multiplying that by y squared, which as I showed earlier is 9t squared s squared, so 9 times 9 is 81, t squared is just on its own, but then s squared times s is s cubed. So altogether, you get 81 times t squared times s cubed. And that right there is the partial derivative of w with respect to t. And now we have both of the partial derivatives of w with respect to the different independent variables by using the chain rule. Okay, so to summarize what we've just done here, the chain rule for multivariable functions, where you have two independent variables and two intermediate variables, looks like this, given that you have a multivariable function, w, in terms of x and y, two intermediate variables that are both defined as multivariable functions themselves in terms of two independent variables, s and t, so we have g of st and h of st, there will be two partial derivatives to find, the partial of w with respect to s and the partial of w with respect to t. When you find the partial with respect to s, you take a partial of w with respect to x times a partial of x with respect to s, and then you do the same thing for y. You add the partial of w with respect to y multiplied by the partial of y with respect to s. All right, there are no t's in this formula, it's all s's. But then going down here, when you take a partial with respect to t, then those two partials of x and y are with respect to t, and you still multiply them by the partial of w with respect to x and y. Okay, and you could extend the chain rule here. If you had three independent variables, then you would need to find another partial derivative for that independent variable. Okay, so if there was an independent variable of q for x and y, so if you had a function of st and q, then you would need another partial derivative of w, but with respect to q. Okay, so you would have a third equation to deal with. It would look very similar to these two, except these partials would be with respect to that variable of q. But with that, that is it for this lesson. But if you do want to get some more practice using the chain rule, feel free to check out my examples video for this topic that I'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.